We are now in Chapter 10b, which continues to explore the development of the kinds of storms we have at our latitude, mid-latitude cyclones. And we kind of left off by letting you know that convergence on the surface is depending on the strength of the divergence aloft. Conversely, divergence on the surface is dependent on how strong the convergence is aloft. And this all relates to something called the jet stream. The river of air in the upper atmosphere that steers mid-latitude cyclones from one place to the other is called the jet stream. The jet stream curves as it sort of undulates around the top of the world in waves, as you've sort of seen by now after having looked at diagrams of the global circulation and so on. The curving of the jet stream, coupled with the changing wind speed around what we call the jet streak, which is the core or strongest part of the jet stream, produce regions of strong convergence and divergence along the flanks of the jet. In other words, on either side of the axis of the trough, to the east or the right-hand side of the trough, you're going to have strong divergence aloft, and to the left of the axis of the trough, you're going to have strong convergence of air streams aloft. If the upper level divergence increases so that the surface convergence can't keep up, then the surface low rapidly intensifies. I refer you to figure 10.10a in your book for that. This term that's associated with very rapid surface low pressure development because the convergence on the surface can't keep up with the divergence aloft is often referred to as explosive cyclogenesis, or we call it a bomb. These are terms that are commonly used to describe a rapidly intensifying mid-latitude cyclone. If the surface storm moves out from underneath the maximum amount of divergence in the jet stream core or jet streak, then the surface storm is going to weaken. That shows you panel B, day 2 there. Day 1 are optimum conditions where the surface convergence, or the red L, can't keep up with the divergence aloft, which is that orange core at position D there. Once that surface system moves out from under the core of the jet, then the whole thing starts to weaken. Bottom line is, for a surface storm to develop and be sustained, it needs the proper upper air support. Without it, it's just going to be a wimpy storm, and we're not going to get a lot of wind or rain or snow. This figure shows a nice summary of clouds and weather and vertical motions and upper air support that are associated with the developing mid-latitude cyclone. The dark green on the surface part of the map, where the red L is, and the fronts, that indicates the area where precipitation is falling, either rain or snow. Once again, the bottom line is that ideally the upper level divergence, or this area up here on the right-hand side of your screen, will occur right over where the surface convergence is going on. And those are the ideal conditions for a good, strong mid-latitude cyclone to develop. Now, we've been talking so far in all of Chapter 10 about the polar front model, or the Norwegian theory as it's often referred to, of mid-latitude cyclone develop. We're going to change gears a little bit now and talk about a different theory called the conveyor belt model, which often is another way of explaining how these things work. You have a warm conveyor belt of air in the northern hemisphere, typically up from the south. That moves northward and it's wedged upward. That's the orange arrow that you see there. You have a cold conveyor belt of air which comes in from the east and then wraps around the top of the surface low and then goes back out in the same direction it came from, pretty much. And then as things progress, you have the yellow arrow, which is a drier conveyor belt of air coming in from the west or the northwest, originating high up in the upper atmosphere and high in the troposphere, and then descends rapidly down toward the surface. So the orange is the warm, moist air coming northward. The blue arrow is the cold air traveling westward and then back eastward again. And then the yellow air is the dry air, which is coming down rapidly from the heights of the troposphere, the tropopause, pretty much. If a band of this dry air sweeps into the storm, it produces a clear area, which I'll show you on satellite pictures in a moment, which is called the dry slot. This tends to show up where the mid-latitude storm becomes more fully developed. The next slide I'm about to show you is a visible satellite picture. In fact, I'll show it to you now, of the dry slot. So when you superimpose the elements of the conveyor belt theory of mid-latitude cyclone development onto this satellite image, you can see where the warm, moist air was going from south to north, how colder air with moisture aloft is wrapping around where the surface low is, and the drier air descending from the upper part of the troposphere coming down toward the surface, feeding into the low counterclockwise. That's the dry slot that we're talking about. Now, in light of this conveyor belt model, let's talk about what is often referred to by meteorologists, at least before Sandy hit in October of 2012, the storm of the century, March 1993, absolutely slamming the East Coast all the way from Alabama and Florida and Georgia all the way up to northern New England. And this thing really developed rapidly. The surface low did. Why did the surface low develop rapidly? Because it couldn't keep up with the rapidly developing divergence in the upper levels of the atmosphere, which were associated with the convergence at the surface. So on the 12th of March at 7 o'clock in the morning, this was essentially what things looked like. You had a small wave cyclone in the Gulf of Mexico that moved east-northeastward and intensified as it got to Florida. By the 13th of March, which is what this picture shows at 4 o'clock in the morning, an intense open-wave mid-latitude cyclone was centered right over the Florida Panhandle, which produced severe thunderstorms and tornadoes in Florida, which is actually kind of rare. Yeah, they get thunderstorms in Florida all the time, but usually they're not severe. In just 12 hours' time, the storm was then centered over Norfolk, Virginia, if you can believe that. And then about 15 hours later, it was all the way over northern Maine. So now I'm going to show you another map which shows you these positions. You can see it was a very weak storm off the Texas coast on the 12th of March, a very strong storm on the 13th of March at 4 a.m. right over the Florida Panhandle. Just 12 hours later, it was right near Washington, D.C., and then in another 15 hours, it was over northern New England. So now let's talk about the results of this particular storm, which are really, really quite something. This is another map that shows the intense pressure gradient force involved in this storm. You can see, and these are 4 millibar isobars, like the ones you're drawing on the weather map at the end of problem set number 3. You see how these isobars are basically wound up like a cinnamon roll? This is not a hurricane. It is a very, very intense mid-latitude cyclone. And the stronger, the closer together these lines of equal pressure are, of course, that means the stronger the pressure gradient force. So this is the surface weather map associated with that storm. Now, check out the satellite picture, the color-enhanced infrared satellite picture, which is also associated with this storm as it was centered over the Florida Panhandle. You can really get a sense for how violent weather may have been occurring in association with the cold front, which was basically slicing diagonally across Florida from northeast to southwest, and then all the way down to western Cuba, which is quite extraordinary for one of these to get all the way down to the Caribbean. Here's the upper air map associated with this, and you can really see the strong trough of low pressure. The red barbs over here indicate very warm, moist air coming in from the south, and the blue barbs indicate very cold and strong airflow coming in from the northwest. So warm, moist air coming in on one side of the trough, cold, dry air coming in on the back side of the trough, and this is the trough axis. This is the upper levels of the atmosphere in conjunction with the storm. So you had very strong divergence right in here, in the upper atmosphere, which supported the rapid development of this mid-latitude cyclone. And when it was at its peak, when they had the tornadoes and severe thunderstorms over Florida and the heavy snow in the Appalachians and so on, you can see how the jet streak, or strongest part of the jet stream aloft, was associated with the strongest divergence here, and associated then with the surface low as it rapidly developed. Now, here are some of the results of these storms. Look at these snowfall totals. These are records which have yet to be broken. In some places in the Appalachian Mountains of Tennessee, 5 feet of snow fell. In Mount LeConte, Tennessee, that was a state record for any single snowstorm in Tennessee. And look at the low temperatures that were recorded, the record lows behind this front as the clear cold air came in from Canada, the continental polar air. Temperatures as low as 21 degrees in Mobile, Alabama, and Daytona Beach, Florida, in the middle of March. This is extraordinary. This is a picture of how much snow piled up on the ground near Asheville, North Carolina, during the storm of the century in March 1993. In summary, 318 people were killed in this storm. 48 people were lost at sea. 44 people were killed by tornadoes in Florida. Snowfall and temperature records were toppled all the way from the deep south up to northern New England. All airports on the East Coast were closed except for the ones in Florida. There were even 3 deaths in Havana, Cuba, where the cold front went through and caused a power blackout, which is really quite extraordinary. Now, let's switch to the West Coast, because we're not immune. We get these storms too. This is known as the Columbus Day storm of October 12, 1962, or often is called the Big Blowdown. Not as destructive as the storm of the century on the East Coast in March 1993, but this surface weather map shows how this open wave cyclone barely started to occlude and was actually the remnant of a western Pacific typhoon by the name of Frida that crossed all the way across the North Atlantic and approached the northern California coast. The lowest pressure went down to 960 millibars, which was really quite extraordinary. There were blackouts in Seattle, Washington, Portland, Oregon. Cape Blanco, Oregon had a wind gust to 145 miles an hour. Millions of trees were blown down. If you want to see some photographs of the results of this big blowdown storm, you can click on that hyperlink. I'm going to tell you that I was I was 10 years old, and I remember that I was home from school. In those days, there was no school on Columbus Day when I grew up in Sacramento. And I remember even in Sacramento, the trees were just flailing around everywhere and the branches were falling. It was really a wild storm. So we have them on the West Coast as well. Now, let's really switch gears and talk about Great Plains blizzards, which are often in winter and early spring generated by intense cyclogenesis on the eastern side of the Rockies and the northern plains. The definition officially of a blizzard, according to the Weather Service, is when wind speeds are sustained at 35 miles an hour or greater, and those winds are accompanied by either falling snow and or blowing snow, reducing visibility to less than a quarter of a mile. This is very bitterly cold continental polar and continental Arctic air that can come down. Cattle and people can freeze in their tracks. People are stranded in their homes for days, maybe stranded in their cars, which is dangerous. Highways are closed. This map shows you areas in the Great Plains where blizzards are more likely to develop. How about this? Here's a picture of the results of a blizzard on January 26, 1978, across the upper Ohio Valley and the upper Great Lakes. If you live in those places, you got to make sure you've got plenty of food to last you for about a week, because you may not have any assistance from public officials with respect to rescue and recovery. So you have to sort of take care of yourself for a while. You can tell when a blizzard is developing in this pattern when you have a telltale wraparound band of clouds on satellite imagery, which I will show you in just a moment. In this blizzard, April 6, 1997, up to 3 feet of snow fell in North Dakota and South Dakota. Wind gusts of up to 60 miles an hour recorded, 20-foot-high snow drifts, $21 million in damage. 10% of the cattle in North Dakota were killed. Later on, it got warm a week or two later, very warm, and all that melting snow caused major flooding in Grand Forks, North Dakota. Here's a surface weather map from that April 6, 97 storm, and also a satellite picture showing the telltale wraparound band of clouds, which indicates that a blizzard is in progress in the northern plains. And here is a picture of that flooding because of that melting snow in Grand Forks, North Dakota, as the Red River jumped its banks in April of 1997. A polar low, we won't spend a lot of time on this, is a unique kind of non-tropical cyclone that develops poleward or behind the polar front. Now, even though the diameters are less than 600 miles, they can have intense winds, and satellite images show these intense eye-looking cloud masses with spirals around them, almost looking like a hurricane, but it's not a hurricane because hurricanes are tropical cyclones, which we'll explore in a future chapter. So here is a picture of an intense polar low in the Norwegian Sea west of Norway. This concludes Chapter 10, PowerPoint, narrated lectures. I hope you learned something about mid-latitude cyclones.